Okay, are we ready now? Everybody good now? All right, I'll take that as a yes. So we are talking about cardinality, and specifically the question of cardinality of n versus the cardinality of r. Is it the natural numbers versus the real numbers? We talked last time about what the cardinality means. Remember, we write like this with this little squiggly thing. This means that A and B have the same cardinality, which means, you know, you think of that as meaning they have the same number of elements, but what this means is there is a one-to-one correspondence from A to B. All right, and in that case, it means that A and B must have the same number of elements, and we write it like that. A has the same cardinality as B. Hopefully I can do this without writing off the side of the screen. All right, we gave several examples last time. For instance, we showed that the natural numbers has the same size as just the even integers, or the even natural numbers at least. And then we also showed for some real number sets that they have the same size. Like this is the closed interval from -1 to 1, and it has the same size as the closed interval from -10 to 10. That's because you can make a function which takes values in this interval and gives you answers in this interval, and that function is 1 to 1 and onto it. Like this function is f of x equals 10x, right? It takes this interval and sort of blows it up into that interval. And this you can show without much trouble at all is a bijection. All right. I had you guys do at the end last time an example showing that this -1 to 1 is the same cardinality as 0 to 1. All right. Here's another example. This is a little weirder, but it is true that, I'll say also, the interval minus pi to pi, sorry, I meant pi over 2, minus pi over 2 to pi over 2, the closed interval, is the same size as all of R, the entire set of real numbers. What you need is a function which takes values in this domain and gives you answers in the real numbers, minus pi over 2 to pi over 2. So I'm going to draw a graph of such a function. Minus pi over 2. Sorry, I made a typo here. This, I do not mean the closed interval. I mean the open interval. Actually, what I wrote is still true if you use the closed interval, but I meant the open interval. Sorry about that. These are roundy parentheses, the open interval. Okay, I'm trying to write a function whose domain is just the open interval here, not including those two endpoints, and whose codomain, and actually equal to the range in this case, because it's going to be surjective onto, is all of the real numbers. Does anybody know such a function? Actually, there is a function like this that you know already, where it goes from here to here, and the range is all real numbers. Anybody, is this ringing anything sound familiar about this? I'm looking to the side at my screen of Zoom participants. All the names.
Tanix, maybe.
Say it again.
Tanix, maybe.
Tan x, he said. Yeah, the tangent. F of x equal tangent of x. Anyone remember what the graph of this looks like? Well, it has these as asymptotes. And the graph of the tangent looks like this. All right. You know, and the tangent, it has more of these things. But if all I care about is this interval, minus pi over 2 to pi over 2, this is a graph of the tangent. And this is a bijection. It is a one-to-one correspondence. You can see it is onto because every real number comes out as one of the answers here, as one of the y values. And it is also one-to-one because every x value has only one y value associated with it. Sorry, I meant every y value has only one x value associated with it. So all this to say, this is a one-to-one correspondence. So in terms of the sizes of infinite sets, these two things are both infinite sets, this interval and the set of real numbers. They have the same size though, because you can stretch this out sort of to this whole size by using this tangent function. All right. Any thoughts about that? Questions? Really what we would like to talk about this time is this n versus r. The question, can there be a bijection from n to r? These are each of infinite size, but it turns out, something I think I said this last time, actually these have different sizes. It is a fact that there's no bijection which takes you from n to r, and we're going to see that in a little bit. Here's a definition, first of all. There are two different sizes of infinity here, and we have sort of a name that we use to distinguish them. So if we have some set, if S is a set with S squiggly n, remember this means S has the same cardinality as n. Sometimes people say S is equinumerous with n, meaning they have the same number of things. If S and n have the same size, if S is a set where S is the same cardinality as n, then we say S is countably infinite. Countably infinite. It means, yeah, it's infinite, but it's like infinity in the sense of things which you can count one after another, all right? We call it countably infinite because that's what describes the size of n. It's infinite, but it's still infinite like counting forever. Versus R is infinite, but it's even bigger than things that you can count. That's the idea. So we say S is countably infinite, or more often we just say countable. So when I say a set is countable, it just means it has the same size as the natural numbers. And something which is not that same size, so if S is infinite, but S is not the same size as n, then we say it is uncountable. Uncountable, all right? So there's like two types of sizes of infinity. One is countable, that is the same size as the natural numbers. And then anything else we call uncountable, bigger than the natural numbers, I guess. Countable, remember what countable means is there's a bijection with the natural numbers. Another way of saying that is that countable, if I have a set called A is countable, means it means you can sort of write out the numbers in n, 1, 2, 3, 4, and it means these can be made in a one-to-one correspondence with the elements of A. I'll call them A1, A2, A3, A4, right? If there is one of these bijection, one-to-one correspondence, that means you can make some kind of a list like this of all the elements of A. You can make them in a list, and those elements are each one just like matches up with one of the natural numbers. All right, this is another reason why we say this is countable. It's like you can write down all the elements in a list. So countable means, I'll just say i.e. you can write all elements of A in some infinite list. So countable means it's infinite, but you can actually write some kind of list, one after another, of all the elements. Uncountable, I suppose, would mean that's impossible. Like it's infinite and also so big that you couldn't even write all the elements, even if you wrote them in an infinitely long list. That should seem a little weird that that's even possible, but we'll see in a few moments. It really is possible. From this point of view, you can say a lot of other sets are countable. If I want to describe, or if I want to explain why something is countable, it's enough to just write down an infinite list which contains all the elements. So for example, Z, the set of integers, so this is all whole numbers, positive and negative. This is countable since this is a list. All you have to do is demonstrate how you could write down an infinitely long list which includes all the numbers. And if I want all positive and negative numbers, you could write it this way. 0, 1, minus 1, 2, minus 2, 3, minus 3, etc. Right? I hope you see the pattern. And here, it should be clear that every integer does appear somewhere in this list. Therefore, this list is an exhaustive listing of all the elements of Z. And so Z is countable. That's what it means to be countable. It means you can make a listing, one after another, of all the elements. All right. Any questions about that so far? This is what countable means. All right. Let's talk about Q. Q is also countable. This is kind of a surprising fact, maybe. Q is also countable. This is the set of all rational numbers. Why this should seem a little surprising is just because Q, there's so many rational numbers, like in between every integer. In fact, there's infinitely many rational numbers in between all of these. Could you really make a single list which you can guarantee includes every single fraction? That's what the rational numbers are. Can you make a single list which includes every fraction? Actually, you can. You got to be a little cute about it, but here's how you could make a list. First of all, I'll write 0. In terms of fractions, 0 is kind of a special one because it has so many different ways you can write 0, and it only has a positive and a negative. It doesn't have a positive and a negative version of 0. Anyway, 0 goes first. And then I'm going to write down all of the fractions. Think of it in terms of numerators and denominators. I'm going to write 1, 1, and minus 1, 1. These are fractions for which the numerator and denominator sum up to 2, all right? And then I'm going to make a list of all the fractions where the numerator and denominator sum up to 3. I'm thinking just in absolute values, ignoring the minus sign. So all the fractions in which the numerator and denominator sum up to 3 would be, oops, 1/2 minus 1/2. I'm always going to include the negatives. And then 2 over 1 and minus 2 over 1, right? These ones, they sum to 3. And I'm just going to continue the list in this way. If you continue listing in this way, then every possible fraction must appear in the list, right? Even something like 22 over 7. Those numbers sum up to 9. And so that will eventually occur in the list once I get all the way down to the ones which sum up to 9. Maybe I'll continue down here. I hope you can see this much. The next ones which sum up to 4, I would say 1/3 minus 1/3. Is that on the screen? Yeah. 2 over 2 minus 2 over 2, and 3 over 1 minus 3 over 1. I believe those are all the fractions you can make where the numerator and denominator sum up to 4. And there's a little subtlety that we need to take care of here, and that is that 2 over 2 already appeared in the list. You can't list the same element more than once because that's like a function which is not one-to-one. So if that ever happens, I just exclude those elements. So basically, you're going to throw away any fractions which are not in their reduced form by the time you get to them in the list, all right? Because those are ones which will have already occurred earlier on in the list. But anyway, this will be a list. If you continue writing, you can continue writing this as much as you want. I'm not gonna do any more. I'll just say ... Every rational number appears in the list, and therefore the set of all rational numbers is countable, right? So You know, at the very beginning last time, I think I brought up the basic question about sort of different sizes of infinity. We had n versus q versus r. What we've just demonstrated is that these are the same size, right? If you're talking about sizes of infinity, the size of the natural numbers is the same as the size of the rational numbers. But I'm here to tell you, I'll write this as a theorem because we're going to do the proof. It's actually, the proof is not so, it's not really hard to understand. It's hard, it would have been hard to come up with this proof, but this is a theorem. This was proved by Cantor in the 1870 something. Did I write it down? No, 1870 something. Cantor was the first person to really think of all of these ideas about countable, uncountable, and measuring the sizes of infinite sets. Cantor's theorem is simply that R is uncountable. R is uncountable. We have to, what's difficult about this is we have to somehow demonstrate that R cannot ever be listed. All right, let's see if we can do this. We're going to do the proof by contradiction. So I'm going to say, for the sake of a contradiction, we assume R is countable. I just wrote a box. Assume R is countable. And that means that we can make a list of things, an infinitely long list, which includes every real number. So I'm going to say, so because of this, based on this assumption that R is countable, we can write a list. R is x1, x2, x3, etc. All right. And from here, we will derive a contradiction. And wouldn't you believe it, Cantor's proof uses, this is the final one of our basic properties where we use the completeness axiom. We're going to use the completeness axiom. Actually, we're not going to use the axiom of completeness directly. We're going to use the nested intervals property, the NIP. Remember the nested intervals property. It says any intersection of infinitely many nested intervals, nested closed intervals, is not empty. That's the nested intervals property. We're going to use the nested intervals property based on these numbers. So how do you take a listing of all the real numbers and somehow turn that into a bunch of nested intervals? That's the trick that Cantor thought up. We take all of those numbers and turn them into a bunch of nested intervals. I'm going to try and maybe draw a picture here. So this is all of R, right? And we have those numbers. Apparently, every number occurs in this list, and they go like, maybe here's x1, here's x2, here's x3. I intend for this to be just sort of, we have no idea where they go, right? Here's x5, let's say here's x6, all right? Our assumption is simply that you can make a list of all the real numbers. So that list, they just go somewhere, right? I'm going to build some nested intervals out of these numbers. So we're going to choose, maybe I'm going to try and sort of draw the nested intervals up here, but I'm going to give you my commentary down here. I'm going to say let I1 be any closed interval. This is my first of the closed intervals. I wrote interval with 2 R's. Let I1 be any closed interval containing x1. All right. So let's say on this picture, maybe it's like that. Maybe that's what I1 looks like. Okay. And then I'm going to say how you shrink the interval every time. I'm going to say let I2 be how about, let me say it differently than that, sorry. For I2, shrink I1 on one side until it excludes x2. Did I go off the side there? I said until it excludes x2, all right? So to get the second interval, I2, we're gonna shrink the first one on one side until it excludes I2. So until it excludes x2. So I start with this I1. To get I2, I'm gonna shrink down the left side, bring it sort of over here. This is I2. So, and we're gonna continue this procedure. Every time, every step, we are shrinking the interval on one side or the other, and it doesn't matter which side, in order to exclude another one of the real numbers in this list. So for I3, I shrink I2 on one side until it excludes x3. So maybe I'll shrink the right-hand side next time. I lined it up there, so x3 is no longer in this interval. All right, we're going to continue to do that. What would I4 look like? Actually, x4 is already excluded from I3, so in that case, we'll just make them the same, I4, right? And then I5 will have to shrink down to exclude x5, so maybe I'll start it over here now, I5, etc. All right, these are the nested closed intervals. Each one is built specifically so that it excludes one of the points in the list, all right? Sorry, I gotta erase this picture here. I don't have a whole lot of space. Oh, that was my ding, I got an email. So because of our construction, so for example, I'll say e.g. I5 excludes, sorry, I'm getting more and more emails. I'm gonna turn off my email program. For example, I5 excludes x1, x2, all the way up to x5, right? All the way up to x4 is the way that I did this. I5 was constructed in order to exclude x4, but it also excludes all the other ones because it's nested with the previous ones and they excluded all the other ones too, all right? Okay, anyway, now because of the nested intervals property, by the nested intervals property, we have intersection n equals 1 to infinity. In is not empty, right? That's what the nested intervals property means. So after you continue chopping this interval down over and over again, you will end up with something, at least one number in this intersection. So I'm gonna say, let's just say x is in the intersection. All right. So x is in every I sub n. That's what it means to be in the intersection of all the INs. X is in every IN. And what does that mean? You have to think about how the INs, every IN was chosen to exclude a bunch of the X's. Actually, this means if X is in every one of these IN, then it means that X is not equal to XN for any n, because IN is always chosen to exclude the first n x's. And if x is in every one of them, if you have one point which is in all of these, it must not be equal to any of the original marked points on the line, because these guys are chosen to omit the marked points one after another. All right, does anyone see how this is a contradiction? This actually does result in a contradiction. Can anybody say? I know I haven't asked you to chime in lately. Can anybody hear me? Is anybody out there? I think you're there, but nobody's saying anything. Can someone at least say, yes, I hear you?
We hear you.
I hear you.
Yeah, you're just not saying anything.
Wouldn't it be a contradiction because if x is in every IN but you're shortening the interval every time, then that wouldn't be possible?
We are shortening the interval every time. That's right. Although, I mean, it is sometimes possible to shorten the interval every time. Like we did all those examples a few times ago. If, for instance, we left one of the ends the same every time, then that point would be in the interval. Or if it shrinks but doesn't go all the way down to a single point. Thank you for saying something, by the way. It is possible in theory for some point to be in the entire intersection of all the intervals, but the contradiction has to do with the assumption that we made at the very beginning. Remember, we assumed that we could produce a list of every real number, right? We had assumed, I might as well write this down. We had assumed that R is equal to x1, x2, x3. So every real number is in the list somewhere, right? Does that give anybody any ideas? Why is this impossible? Or at least it's incompatible with what we said up there.
Since we said x is not equal to xn, that is contradicting that it's in the list.
Yeah, right. Our original assumption here is that R is equal to the list. That is, every real number appears in the list, right? That's what this means. We had assumed that R is countable, which means you can write down a list which includes every real number. But we just found a real number inside the nested intervals, which apparently is not in the list, all right? So I'm gonna say we assumed that R was equal to the list, but we found X, which is a real number, but X is not in the list. This is the contradiction. Sometimes people write this to indicate a contradiction, little two arrows hitting each other. Or there's sometimes people write a little, it's supposed to be like a lightning bolt or something. I don't know. This is the contradiction though. We assumed that there was a complete listing of every possible real number, but then you do this cute little nested intervals thing and you end up finding a number which is not part of the list. And that's the contradiction. The moral of the story is no list is big enough to contain every real number. Even if the list is allowed to go on forever, it will always exclude some real numbers, all right? So R is countable. So you can tell this to your friends. Tell your mom over dinner that the size of the natural numbers is strictly less than the size of the real numbers, right? These are both infinite quantities. They're called in this study they're called transfinite cardinals. They are both cardinalities which are not finite, but the natural numbers is lesser than the real numbers. These ones you can make a list. These ones you cannot make a list. Any listing of the real numbers would automatically omit some. And so these are bigger. Pretty great fact in my opinion. This, like I said last time, this is one of my favorite facts in all of mathematics. Not just the fact of it, but the fact that people were actually able to figure this out. It seems like a real kind of deep thing to me, at least, to talk about different sizes of infinity. I would like to, if you are talking to your mom about this over dinner, your mom is likely unfamiliar with the nested intervals property. I don't want to make assumptions about your mom. My mom was a math major, actually. She probably now does not remember the nested intervals property, but I'm sure she knew it at one point. And maybe your mom did too, but most people don't know about the nested intervals property. Actually, Cantor came up with another proof of his uncountability of the real numbers. This one actually you could explain to your mom or anybody else, your dad or your grandma, if you like. Here's another way. I will say this is a cuter proof that's based on decimal expansions. And this one, anybody would be able to understand. There's some points of it that are slightly less technical that I don't want to get into the details of, which is why I didn't just say this one and skip over the other one. This one, actually, Cantor did this one in the I think I wrote this down, in the 1890s. So he did his original proof using the nested intervals property. Like what we just discussed is more or less what Cantor wrote in the 1870s. But then he was like, I got one more for you guys. 20 years later, he came back with another proof. I said it was controversial. It was controversial, although by this time it had kind of settled in a bit. But Cantor gave another proof. Check it out. Here's this is one that you could explain to all your friends. Again, for the sake of a contradiction, assume we have a list of all real numbers. A list of the numbers R. So something like R equals x1, x2, x3, and so on. All right. And let's just imagine that you take this listing of numbers and write them down in their decimal expansions. And I'm just going to make up sort of a made up example. So write the decimals. Now your hypothetical list, I don't know what order you're writing these things in. I'm going to erase this because I need more room than that. I'm going to try and just write down the decimals for all the numbers in the list. So maybe x1, maybe it starts with 1 as a decimal. Of course, this is 1.00000, etc. I'm going to write 6 digits of each one. All right, let's say x2 maybe is pi. That would be 3.14159, etc. Let's say x3, what did I say? I'm just making these up at random. It doesn't matter what they are. Let's say x3 was 8.67530. And recognize this is one of my favorite numbers, 86753. You know the next digit? Nobody's saying it.
9.
9, yeah, look it up. Get yourself educated. Let's say the next one is, how about 7 1/3 maybe, right? Some of these could be irrational, some could be rational. I'm just going to write, it doesn't matter what it is. Maybe this one is 1.23456. The decimal point doesn't always go here. Of course, most real numbers, the decimal point won't go there. Maybe we have 97, how about 975.362. You can put the decimal points wherever you want. I want to write them down though so that the digits are all kind of lined up in this way. All right. And now, just based on this chart here, and this list of course goes on forever, Cantor described a way to create a number which is not anywhere in the list. So what you tell your uncle who doesn't know anything about math, if you're trying to convince him of this, you say, okay, Uncle Bob, if you think it's possible to write all the real numbers in the list, all right, write them down, write them in like a grid like this, line up the digits, and I will tell you a number which does not occur anywhere in the list. Here's how you do it. Cantor calls this a diagonal argument. You look at the numbers along the diagonal like this, all right? And I'm going to create my new number by just increasing each digit on the diagonal by 1. So I will get 2, and I might as well, I'll put the decimal point right there. 2.274. What I didn't do what I said. Increase the number by 1. And if it's a 9, then just roll over and put a 0. So this 7 becomes an 8. This 3 becomes a 4. 5 becomes a 6. 2 becomes a 3, etc. All right. And I'm here to tell you folks, this number cannot appear anywhere in the list because this number is specifically designed to be different from every number in this list in one of its digits. All right. So it is a fact.
You wrote a 2 by accident.
I wrote it. I wrote the same one. I say thank you. 3 is what I meant. You increase the digit by 1 every time. All right. And if you do this properly, my new number x is different from each number xn in digit n, right? Like x, the first digit is different from the first digit of x1. So x cannot equal x1. The second digit of x is different from the second digit of x2. So x cannot equal x2. And so on. I did this forever. It's different from every number in the list. And this is why R cannot be written in a list, because you can do this. You might wonder, can't you do the same thing with Q? Can't you just, if you make a list of all the rational numbers, can't you also make a new number which is not in the list? The answer is yes, you can, but the new number you make is not guaranteed to be rational. In fact, it will certainly not be rational because it's constructed in such a crazy way. The new number you make will not be expressible as a fraction. All right. I said there was some subtlety behind this, which is why I didn't just give you this as the first proof. The reason is because decimal digits are actually kind of weird for real numbers. You may know that specific real numbers have more than one way to write them as decimals. For instance, the number 1 can also be written as the number 0.9 repeating. Those are equal, even though they differ in their decimal digits. So this is not quite technically airtight, although you can make it, you know, when Cantor presented this, he did all the, there's some extra work you have to do about ambiguity of decimal representations, which I don't really want to get into. But this is Cantor's diagonal argument, very famous proof, and pretty convincing if you ask me, and pretty cute. Like, I think there's something very kind of, there's a lot of ingenuity that goes into designing this this argument. Any questions about that? The diagonal argument, important in my opinion in the history of human thought. Yeah, I went there. I'm not afraid to go there. We got 10 minutes left. I thought maybe I would tell you a few more things related to this work that Cantor did, and then we'll start off next time going into something completely different. So actually, Cantor actually showed, and this was in his original paper in the 70s, the 1870s. Cantor actually showed that the size of S in terms of infinite cardinalities, the size of S is strictly less than the size of this P of S, where I hope maybe you remember from discrete math, P means the power set. That is the set of all subsets of S. So if S is an infinite set, the power set is always a larger cardinality than S. And certainly this is also true of finite sets, but more interesting in terms of infinite sets. The power set of S is always larger cardinality than the original set S. So that means actually we can create many sizes of infinity. For example, we have n to begin with, and then we also have the size of the power set of n, which Cantor actually used the same kind of diagonal trick to demonstrate the power set of n is strictly bigger. So this size of infinity is different from this size of infinity. The power set of n, this would be the set of all subsets of natural numbers. This is a little weird, but actually it's not so hard to show that this is the same as the size of the real numbers. And they're different though. The n is this is countable, this is uncountable. But this, you can continue, do the power set of that again. All right, and we have yet another larger infinite quantity, right? This is countable, this is uncountable, this is even bigger because Cantor showed that always when you take the power set, it makes it bigger. And so the power set of n, this is a very weird set, but it is of larger size than the power set of n. So actually, I said there are two different sizes of infinity. Actually, there's not. There's well, at least three, right? You can do this. Any thoughts about, are there more than three sizes of infinity? The real question I guess I'm asking is how many infinities are there, right? Anyone want to say? What do you think?
Are there infinitely many infinities?
Yeah, infinitely many. You can do this as many times as you want, right? I just wrote 3 of them, but of course you can put another P in there and you get another one. Yeah. I just say infinitely many. This is a question your friend on the playground is unlikely to ask you if you tell your friend on the playground that there's more than one size of infinity. Their mind might be so blown that they don't know what to say next, but really what they should ask you is, oh yeah, well, how many are there? And you say, there are infinitely many sizes of infinity. Your friend actually, if they're very insightful, they might ask you yet another follow-up question. Anyone have another follow-up question? This is a very insightful follow-up question. When I said there are infinitely many, which infinity did you mean? Are there countably many sizes of infinity? Are there uncountably many? Are there like this many or this many?
Is it uncountable?
It is uncountable. In fact, it's not even uncountable like this much. It's actually more infinite than any of these. So this is very strange and a very deep fact, which I must confess, I'm not a mathematical set theorist. This is not really my my thing. So I don't know all the details about these very deep questions about the size of infinity, but I know enough to say this. The number of, the word they use for this is transfinite cardinalities. The number of transfinite cardinalities, that is how many different infinities are there? The number of transfinite cardinalities is larger than the cardinality of any set. So the infinity that describes how many infinities there are, it's more than the number of things in N. It's more than the number of things in R. It's more than the number of things in power set of power set of power set of N or anything. It's actually large, more than the number of things in any set. This is actually something which traditional set theory as described by Cantor is not capable of expressing how many different infinities there are. There's sort of too many, more than any set. So you could never make a bijection from this quantity to any set. The short answer to your friend on the playground is a lot of infinities. There's like larger than you can imagine as far as how many different sizes of infinity there are. This is kind of mind-blowing to me, at least. I don't know if you're into this, but to me it is pretty crazy. One more kind of mind-blowing thing that Cantor described. All of this were questions that Cantor raised. Actually, I don't believe that Cantor tried to settle this question himself, but there was another question that Cantor asked. So we know that n, the size of n, is less than the size of r, right? A question that Cantor asked is there any set which is in between here? Any infinite cardinality which is bigger than n but smaller than r? So is there any s with the size of n less than the size of s less than the size of r, right? To me, a natural candidate would be Q, because I think of Q as like an infinite set, which is kind of in between the natural numbers and the real numbers. But actually, it's not in between. We already said Q is countable. So Q does not have this property. Q has the same size as n. It's not greater. Is there any set which fits in between? Cantor, as far as I can tell, believed that the answer was no. And he wrote this. Cantor did not prove this, which is why it's not called a theorem. But he called this the Continuum Hypothesis. That's how you spell continuum, right? Continuum Hypothesis. And this was in Cantor's original paper in the 70s, the 1870s, the Continuum Hypothesis. It just says there is no set S having its size like intermediate in between the naturals and the real numbers. Cantor wrote this, and it's called a hypothesis because he didn't prove it. But by the end of the 1800s, this came to be regarded as the most important unsolved problem in all of mathematics. in 1900, there was a very famous meeting where they kind of, the great mathematician of the day produced a list of all the math problems for the new century, the 1900s, the 20th century. These were problems that he believed would set the tone for all of mathematics in the 20th century, unsolved problems. And the first one on the list was the continuum hypothesis. It wasn't settled until quite a bit later, but I'll tell you what happened. In 1940, a mathematician named Gödel, this is a strange resolution to the continuum hypothesis. Usually I would just tell you somebody proved it in this year, or somebody proved that it was false, the opposite of that. There is something in the middle. Anyway, in 1940, what happened was Gödel didn't prove it, but Gödel showed that the continuum hypothesis, can I just write CH? This is how people often abbreviate the continuum hypothesis. He showed that the continuum hypothesis does not lead to a contradiction with set theory. All right, so Gödel was not able to prove that the continuum hypothesis is true, but he's basically proved that you can't disprove it by contradiction, right? If you assume the continuum hypothesis is true, this cannot lead to a contradiction. This is what Gödel proved. This is kind of weird, but that's what happened in the 1940s. The next big advance on the topic was in the 60s. 1963, a mathematician named Paul Cohen, who is regarded as one of the greats of mathematical logic of all time. Cohen also didn't prove it. Cohen showed that, well, I'll write it this way, the negation of the continuum hypothesis, that is the opposite of the continuum hypothesis, does not lead to a contradiction. All right. And if you take these two things together, what that means is basically you cannot prove that the continuum hypothesis is true or false, because if it's true, that doesn't lead to a contradiction. And also if it's false, that doesn't lead to any contradiction. So the resolution by the 60s, everybody was on board with this as a somewhat strange resolution to an unsolved math problem. The moral of the story is continuum hypothesis cannot be proven or disproven. I'll just say as a caveat, using ordinary set theory, right? That's what Gödel and Cohen both demonstrated. The continuum hypothesis cannot create a contradiction with ordinary set theory, and also the opposite of the continuum hypothesis cannot create a contradiction using ordinary set theory. All right. So is it true or not? The answer is, well, whether it's true or not is kind of inaccessible to proof using mathematics. And this was mathematically proven. So they proved mathematically that there can be no proof of the continuum hypothesis. Very, very strange, kind of shocking result. You know, when Cantor came up with this question, I'm sure he had no idea that it would be resolved in this way. That this theorem, this was actually one of the first major examples of a problem which people had tried to solve for a long time, historically speaking, but it turned out it was impossible. Not that it was true or false, but you can't prove if it's true or false. It might be true, it might be false. You can't prove it using set theory, though. This is sort of a common a joke that a famous mathematician in the 20th century, Paul Erdős, said. His hilarious joke, you can tell this joke to your friends. When I die and go to heaven, the first question I'm going to ask God is the continuum hypothesis true or not? That's the joke. The joke is, this is a question which simply cannot be answered by mathematics. Not because we're not good enough, or we don't know enough, but just there is no mathematical answer to that question. Even though you feel like, is a question, does something or other exist or not? It ought to have an answer, at least. I mean, it becomes a philosophical question at that point. Anyway, the continuum hypothesis, one of the great legacies of Cantor's work, is an unsolved problem which must forever remain unsolved. It is now proved that you can't prove it one way or the other. Pretty crazy. And I think, sorry, I went over by a few minutes. I just get so worked up about it. I think that'll do it for today then.